Before we get started with today's video, I wanted to tell you that I have another channel that I've started recently where I talk about Sudoku puzzles and other related pencil puzzles. If you'd be interested, there's a link down below to the Zeta Math Does Puzzles channel. I stream there once a week, so if you want extra Zeta Math content, feel free to go there. Hello, and welcome to Zeta Math. Last time on Zeta Math, we told the story of how Euler realized that, much like a polynomial, it was possible to factor the function sine of x as a product in terms of its zeros, leading him to discover the fascinating identity sine of x is equal to x times this product as n goes from 1 to infinity of 1 minus x squared over n squared pi squared. Though fascinating in its own right, we used this to motivate Riemann's discovery of a similar product formula for the zeta function in terms of its zeros. That product formula looks like this. Zeta of s is equal to e to some power divided by s minus 1 times the product across the zeros of the zeta function of 1 minus s over alpha times some power of e. We talked at the very end of the last video about how Riemann used this formula to derive an explicit formula that describes the distribution of the primes. Riemann's key insight here was that in order to make this product formula work, he needed to view the zeta function not as taking real number inputs, but rather as taking complex number inputs. Today's video marks the beginning of a series in which we'll seek to motivate the study of the complex numbers and understand Euler and Riemann's formulas for sine of x and zeta of s.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone, but
better. My goal is to convince you that in a certain sense, as soon as we define a real function, we can actually already evaluate that function on the complex numbers as well. In this way, we're going to avoid having to ask what sine of 3 plus 2i or zeta of 5 minus 2i mean. We'll simply be able to assign values to them. We begin our story today with Bombelli, who was perhaps the first to notice that contemplating the complex numbers might yield interesting information about the real numbers. To start, let's recall the quadratic formula, which gives the roots of a quadratic equation in terms of its coefficients. This number under the square root is typically called the discriminant of the quadratic, often denoted by a capital letter delta. And this discriminant helps tell you the nature of the roots of the quadratic. If delta is positive, that tells you that this quadratic has two real roots. If delta is 0, that tells you that this quadratic has exactly one real root with so-called multiplicity 2. If, however, delta is negative, then this formula gives us a square root of a negative number, and so that tells you that the quadratic has no roots. Or, if you prefer, it has two strictly complex roots. The quadratic formula was known even to the ancient Babylonians. But it was not until the 1500s that Cardano discovered a similar formula for the roots of a cubic polynomial. What a mess. You can immediately see why this formula probably wasn't taught to you in school. And I want to do an example for you just to show you that this formula is actually even a little bit worse to use in practice than it might look at first. To do that, I'm going to start with the example x cubed plus 6x minus 20, and we're going to use this formula to calculate a root. Plugging in 6 for p and negative 20 for q, we're left with the cube root of 10 plus 6 times the square root of 3 plus the cube root of 10 minus 6 times the square root of 3. After some reflection, you can convince yourself that the cube root of 10 plus 6 times the square root of 3 is actually 1 plus the square root of 3. How do we know that? Well, just cube 1 plus the square root of 3 and make sure that you get 10 plus 6 times the square root of 3. Similarly, the cube root of 10 minus 6 times the square root of 3 is 1 minus the square root of 3. Plugging those cube roots into our formula, we find that 1 plus the square root of 3 plus 1 minus the square root of 3 is a root of our original cubic. That number, of course, is just 2. It's then easy for us to verify, by plugging 2 into the original cubic, that the formula gave us something correct, because 2 cubed is 8, plus 2 times 6 is 12, minus 20 is 0. The cubic that Bombelli happened upon was x cubed minus 15x minus 4. If you apply the formula above, then the root of this cubic that you get is the cube root of 2 plus the square root of negative 121 plus the cube root of 2 minus the square root of negative 121. Our experience with the quadratic formula suggests that these square roots of negative numbers appearing in the formula would mean that this cubic has no real roots. Indeed, this is what Bombelli expected also, except that Bombelli already knew that x equals 4 was a root of this polynomial. Did this mean Cardano's formula was wrong? What was going on? What Bombelli noted was that if you just pretended that taking the square root of negative numbers made sense, even though everyone at the time knew it was obviously absurd, then you could see that in fact 2 plus the square root of negative 1 cubed was equal to 2 plus the square root of minus 121, and 2 minus the square root of negative 1 cubed was equal to 2 minus the square root of negative 121. Putting these numbers in for the cube roots in the formula, then the formula tells us that 2 plus the square root of minus 1 plus 2 minus the square root of minus 1 is a root of this cubic. But of course, that number is just a complicated way of writing 4, which is what Bombelli had expected. In fact, if you take a step back, in this example the square roots of minus 1 behave exactly as the square roots of 3 behaved in the previous example. The fact that this square root is of a negative number ends up providing no meaningful difference in how all of this works out. Bombelli certainly didn't think of himself as discovering a new number system when he did this. Rather, he just thought of himself as finding a shortcut through the algebra that was able to get the answer to the question that he wanted out of the formula he already had. But once Bombelli had opened the door to thinking about square roots of negative numbers, mathematicians found many, many places where thinking about them helped them answer questions they already had that did not themselves involve anything about square roots of negative numbers.
Bridgestone Turanza 6. The wet handling test involves sudden lane changes on wet roads.
As usual, in this video we're going to visualize the complex numbers as laying in a plane like this, with the real numbers laying on this line, and the strictly complex numbers laying off of this line. For example, 3 plus 4i in this picture would be somewhere over here. We'll also be looking at graphs of real functions, like sine of x, which appear in R2. To avoid possible confusion, we'll always display the complex plane with these grid lines, and R2 without them. The task before us is to take a function like sine of x, or tangent of x, or e to the x, that is defined on some portion of the real line, and figure out a way to meaningfully evaluate it off of the real line. The key word here is meaningfully, because ostensibly there are lots of ways to define this function. For example, I could just define the function on the real line. Or just say, well, ignore the complex part altogether, just take the sine of 2 if someone asks you for the sine of 2 plus 3i, for example. But if we want to be honest and meaningful about it, I want to convince you there's really only one way we can do this. And I'm going to call this process thickening. My goal isn't to immediately define this function in all of the complex numbers. My goal is just to extend this function a little bit away from the real line. So visually, what I'm thinking of here is taking a function that's defined only on the real line and then just blurring it a little bit out so that it's defined a little bit on each side. And then once we do that, then we can go a little bit further and a little bit further and eventually end up defining the function on much of the complex plane. The key observation that drives this process is that if the function I start with is a polynomial, then I can extend it to the complex numbers just using the regular operations of addition and multiplication of complex numbers. For example, if I start with the function f of x is x cubed minus 2x, then evaluating f at a complex number is essentially free. For example, f of 3 plus 2i is 3 plus 2i cubed minus 2 times 3 plus 2i, which you can simplify to minus 15 plus 42i. This really only works for polynomials, though. I can't say, oh, well, if someone asks you to plug 3 plus 2i into sine, just take sine of 3 plus 2i. It doesn't help at all in that instance. One convention you'll often see is to denote a function where you're intended to plug in real numbers with the variable x, and a function where you're intended to plug in complex numbers with the variables z or s. This is why most often when you see people talk about the zeta function, you see it expressed as zeta of s instead of zeta of x. So in terms of this convention, what we've basically said is if we want to take the real function, f of x equals x cubed minus 2x, and turn it into a complex function, all we do is replace the x's with z's. The reason why this is important is that, in essence, every nice function is almost a polynomial already. If that sounds strange to you, essentially, whenever you think about a Maclaurin series or a Taylor series for a function, what you're doing is taking a function and writing it in a form that's pretty close to a polynomial. As a first example, I want to start with the function sine. Sine of x, as we discussed in the previous video, has the Maclaurin series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. If I want to evaluate sine of pi over 6, one way I can do that is to plug pi over 6 into this formula. Of course, this formula has infinitely many terms, so plugging it in isn't so easy, but what I can do is plug it into the first however many terms I want, and then stop. Here in this table, I'll show you what happens if you plug it into just the first term, the first 2 terms, the first 3 terms, and so on. And what we see is that if we plug this into not that terribly many terms, we already get that this is approaching the value of 1/2 that we expect for sine of pi over 6.
Who is a smart trader? Someone who trades with FX Pro.
We can actually see this happening for all real numbers at once if we look at this graph of sine and then plot the partial sums of the Maclaurin series over it. Here's x, and x minus x cubed over 3 factorial, and x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Note how quickly the partial sums hug the graph of sine of x. So how do we evaluate sine at a complex number, like 3 plus 2i? Well, we just do the same thing. We plug 3 plus 2i into each of these partial sums and look at the values, and we can see that rather rapidly these partial sums converge. Just by looking at these values, we can conclude that sine of 3 plus 2i must be some number in the vicinity of 0.53 minus 3.59i. In the case of sine of x, it's actually the case that we can calculate the value of sine of any complex number simply by plugging it into the partial sums of our Maclaurin series and waiting for it to converge. Unfortunately, the situation in general is a tad bit more complicated. To see what goes wrong, let's look at this graph of the real function tangent of x. Note, this isn't the complex plane, this is just our typical R2, where I've graphed y equals the tangent of x. Now, I'm going to graph on top of this the partial sums of the Maclaurin series, x plus x cubed over 3 plus 2x to the 5th over 15, and so on. As we look at these partial sums, we see that they provide better and better approximations of tangent of x, but only in this narrow band. Even for real inputs, my Maclaurin series for tangent of x can't tell me what the value of tangent of x is supposed to be over here. The reason for this is that the graph of tangent of x has these vertical asymptotes. And though polynomials can bend and turn and do all the nice things that we would hope a function would be able to do, one thing a polynomial can never do is have an asymptote. So what happens is that our polynomial approximations of tangent of x do the best they can, and it just so happens that the polynomial approximations can't ever make it past these two asymptotes. These points in the graph that can't be approximated by polynomials are often called singularities. If we try to input complex numbers here, as we did before, we'll find something similar. If I plug in a complex number that's close enough to 0, like 1 plus I, then we see that the partial sums converge, just like happened with sine before. If, though, we try to plug in 3 plus 2i to the partial sums, this happens. Whoops. No matter how many terms of the partial sum I write down, it's just not getting any better. Summarizing what we know so far, the Maclaurin series for tangent converges in the complex plane on this red line. We also know that it converges at 1 plus I, which I'll indicate by turning this point red. Then, we saw that it diverges at the point 3 plus 2i, which I'll indicate by turning this point gray. Let's try a few more. At I, the series converges. At 1 minus 2i, it diverges. Let's try a bunch more examples. From this picture, you might correctly guess that the points in the complex plane where the Maclaurin series for tangent converges take the shape of this disk. So we've done two examples. Sine of x, whose graph looks like this, where it turned out that we could use the Maclaurin series at 0 to evaluate the function anywhere in the complex plane, and tangent of x, whose graph looks like this, where it turned out that we could only evaluate the function at some complex numbers close enough to the origin. I'm going to show you a third function. Here's the function f of x equals 1 over 1 plus x squared. Which do you expect this to be like? Like sine of x? Or like tangent of x? Seeing how this graph has no asymptotes, it would be reasonable to expect this function to behave like sine of x. But as you can see as I graph the partial sums of the Maclaurin series, it only converges on this interval. Remember, this red interval on the graph on the left is this red line in the complex plane on the right. Like I did with tangent of x, I'm going to plug some random numbers into the Maclaurin series of 1 over 1 plus x squared, and mark those where it converges and those where it diverges. Why is this happening, even though we see our function has this nice smooth graph? Well, if we broaden our view here and think in the complex plane instead of the real line, we can see that tangent of x has asymptotes here and here. On the other hand, 1 over x squared plus 1 actually has asymptotes at I and minus I, because if we were to plug I or minus I into this function, we would get 1 over 0. And so what we see happening here is that the region in which the Maclaurin series converges begins at 0 and then grows symmetrically around it until it hits the first singularity. What I find particularly remarkable about this is that the asymptotes of 1 over 1 plus x squared at x equals I and x equals minus I stop the Maclaurin series from converging even on the real numbers beyond minus 1 and 1. In this way, the behavior of this function on the complex numbers is affecting the way the Maclaurin series behaves on the real numbers. It is a general fact that for any reasonable function, its Maclaurin series will converge within a circle whose radius is equal to the distance to the nearest singularity to 0 in the complex plane. The reason why the sine of x example from earlier did not run into any of these problems is that the function sine of x is entire, meaning that it has no singularities anywhere in the complex plane. The function zeta of s that we're most interested in has a singularity here at s equals 1. This shows up as an asymptote in this graph of zeta on the real line. Another thing apparent in this graph, though, is that the function zeta of s, defined by this series, doesn't even make sense for s less than 1. Thus, the function zeta of s doesn't have a Maclaurin series at all. Fortunately, our cure here is relatively simple. We just need to change our perspective from thinking about things centered at 0 to thinking about them centered at some other point. You might recall from your calculus classes that this idea is usually known as a Taylor series. Instead of writing down the Maclaurin series, which has the form a0 plus a1x plus a2x squared, and so on, we're instead going to write a series of the form a0 plus a1 times x minus x naught plus a2 times x minus x naught squared, and so on, where we've shifted our center now from x equals 0 to x equals x naught. In a Maclaurin series, if x is very close to 0, all of the terms are small, because powers of small numbers are small. In a Taylor series, all the terms are small, not if x is close to 0, but if x is close to x naught, because that makes x minus x naught small. What's now true is that if we start at any point x naught on the real line, write down the Taylor series at that point, then that Taylor series will converge in the complex plane in a circle around x naught, whose radius is equal to the distance to the nearest singularity to x naught in the complex plane. As an example, let's look at tangent again. The asymptotes of tangent are here at pi over 2, 3 pi over 2, and so on. Let's try to evaluate tangent of 3 plus I. I definitely cannot use the Maclaurin series for tangent to do this, because 3 plus I is further away from the origin than this asymptote at pi over 2. However, if instead we take the Taylor series for tangent of x centered at x equals pi, and then plug 3 plus I into the partial sums, we find that it converges rapidly, and conclude that tangent of 3 plus I should be approximately negative 0.06 plus 0.76I. So here's a summary of how we start with a function that's defined on the real line and get a function that's defined at least around the real line in the complex plane. Namely, at each point on the real line where our function is defined, we take its Taylor series, and we use that to define the function in a circle around that point. We do this at every point on the real line, and thus we end up defining our function, again, at points near the real line. Remember that calculating the Taylor series only requires calculating the derivatives of the function, and for that, we only need information about the function on the real line. And from that, we can just define what the values of the function should be in the points of the complex plane.
My work is easy because I use ClickUp. Here's how I keep track of all my tasks. I start by brain dumping everything I need to
Essentially, we can think of it as that those values of the function in the complex plane were there the whole time. Key features on the function, but a tiny piece of the real line are sufficient numbers defines tangent within this disk. 3 plus 2i is over here, outside of the disk, but 3 plus I, as we saw before, is in the disk. So we write down the Taylor series of tangent at this point, which will now allow us to define tangent anywhere within this disk, which does include 3 plus 2i. And that will allow us to define tangent of 3 plus 2i. Now that all sounds so natural that you might not even notice that what I just said requires us to take the derivatives of functions at complex numbers, which initially sounds quite scary. The reason why we need those derivatives is that our formula for the Taylor series of a function is the sum as k goes from 0 to infinity of the kth derivative of f evaluated at x naught over k factorial times x minus x naught to the kth power. So we need not just even the first derivative of our function at 3 plus I, but we'll actually need all the derivatives of our function at 3 plus I so that we can evaluate tangent at 3 plus 2i. But this is where we come to one of the very best parts about the way that we've made complex functions out of real functions. We're going to get the derivatives of these functions at the complex numbers for free. Why? Well, ultimately, because we know the power rule. So, for example, if I want to know the derivative of sine of x at 3 plus 2i, then what I do is I take the derivative of x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and so on. That just requires the power rule. And I get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. And I can just plug in 3 plus 2i to the partial sums of this power series, and I'll get that the derivative of sine at 3 plus 2i is approximately negative 3.72 plus 0.511i. This same method works just as well for the second derivative and the third derivative, and so on. Over and over, all we have to do is apply the power rule. And so when we talk about thickening the values of a function away from the real line into the complex plane, we're actually not just thickening the values of the function, we're also thickening its derivative, its second derivative, its third derivative, and so on. And all of that comes for free just from the way that we chose to define this function on the complex numbers. And so, going back to our tangent example, I started by taking the Taylor series for tangent at pi, which allowed us to define not just tangent, but all of its derivatives inside this disk. Knowing all of the derivatives of tangent within this disk allows me to write down the Taylor series of tangent here at 3 plus I, which will then allow me to define tangent and all of its derivatives within this disk. And this disk now includes 3 plus 2i, and so I can now define tangent of 3 plus 2i using that Taylor series at this point. This process of using Taylor series to repeatedly extend a function into the complex plane is called analytic continuation. This is particularly interesting in the case of the zeta function, which, remember, we originally only defined for real inputs greater than 1.
Me staring at 23 unread messages knowing each response will take 10 minutes to type. We've all been there, typing, deleting, retyping. Now I use Whisperflow. I just think out loud and it creates perfect formatted text on any app or website. Whisperflow understood what I was trying to say and gave me the exact output I wanted. Check out the difference between this same sentence being dictated into Siri versus Whisperflow. Let's meet at 12 p.m. at Joe's Pizza. Wait, no, actually I can't do 12, so let's do 12:30. And instead of Joe's, let's go to Kelly's Diner. Whisperflow understood what I was trying to say and gave me the exact output I wanted. For longer texts like this email, it even formats it professionally so it's ready to go with no editing. So much faster than typing. Whether you're writing in Gmail, ChatGPT, iMessage, WhatsApp, Slack, Cursor, or anywhere else, break free from your keyboard. Do you know how much time you'll save if you quadruple your typing speed? Try Whisperflow for free on desktop and mobile.
Bởi vì khóa học này mình sẽ dạy tiếng Anh như 1 cộng 1 bằng 2, nó rất dễ, không gì khó cả. Nhiều bạn hỏi mình là có yêu cầu đầu vào không? Thì mình nói vui một chút thôi nhé. Khóa học này yêu cầu đầu vào 3 yếu tố rất đơn giản thôi. Cả nhà nghe nhé, 3 yếu tố rất đơn giản thôi. Một là cộng trừ nhân chia từ 1 đến 10 thành tạo. Nên khi mình hỏi cả lớp là 3 nhân 4 bao nhiêu, cả lớp cứ comment bình thường để mình biết trình độ cả lớp nhé. Ô, sao nhiều bạn lại cười, đúng mà. Bởi vì khóa học này mình sẽ dạy tiếng Anh như 1 cộng 1 bằng 2, nó rất dễ, không gì khó cả nhé. Là cộng trừ nhân chia thành tạo. Ok chưa? Nào anh em cộng trừ nhân chia từ 1 đến 10 thôi, không cần yêu cầu cao đâu. Xong yếu tố đầu tiên nhá. Thứ hai là hiểu tiếng Việt, cả lớp nhé, hiểu tiếng Việt. Đấy, yêu cầu số 2 hiểu tiếng Việt. Anh em đủ yêu cầu số 2. Ô, các bạn yên tâm nhá, các bạn hiểu tiếng Việt. Mình sẽ giúp các bạn hiểu tiếng Anh để tiếng Anh giống hệt tiếng Việt. Mình nói thật đấy. Và thứ ba là gì ạ? Yêu cầu số 3 là gì ạ? Nắng mưa biết đi vào trong nhà. Mình là Nguyễn Tiến Đạt, cựu sinh viên trường Đại học Bách khoa Hà Nội, ra trường sớm 1 kỳ và từng đạt 9/9 kỳ học bổng. Hiện tại mình đang là giám đốc của trung tâm Anh ngữ xét. Trong suốt 8 năm qua, hàng trăm hàng nghìn người đã tham gia vào chương trình chinh phục tiếng Anh chỉ với 3 công thức của mình và họ đã có những tiến bộ vượt bậc chỉ trong một thời gian ngắn. Và ngày hôm nay bạn có thể là người tiếp theo. Đặc biệt với sứ mệnh phổ cập tiếng Anh đơn giản tới mọi lứa tuổi và khắp các vùng miền trên lãnh thổ Việt Nam, mình sẽ tổ chức buổi học thử online qua Zoom hoàn toàn miễn phí. Trong buổi học thử, các bạn sẽ được tiếp xúc với phương pháp tiếng Anh độc quyền, chinh phục tiếng Anh chỉ với 3 công thức. Phương pháp này đã được đăng ký bản quyền tác giả tại Cục Sở hữu trí tuệ Việt Nam và cũng rất vinh dự được lên sóng đài truyền hình quốc gia VTV. Chỉ với 3 công thức, bạn sẽ thấy tiếng Anh đơn giản, dễ hiểu và logic hơn bao giờ hết. Tất cả những gì bạn cần làm là ngay bây giờ hãy bấm vào nút đăng ký ở phía bên dưới này. Mình đã mất 3 năm để nghiên cứu, còn bạn chỉ mất 3 giây để đăng ký, sẽ giúp bạn tiết kiệm được 5 đến 7 năm học tiếng Anh đó. Hẹn gặp lại bạn tại buổi học thử xét chinh phục tiếng Anh chỉ với 3 công thức.
It turns out that the asymptote at s equals 1 is the only singularity of zeta of s. So if I pick some point here like 2 and write down the Taylor series of zeta of s at 2, then that allows us to define zeta in this disk. Now, if I hop up to this point, I can find the Taylor series here and use that Taylor series to define the zeta function in now this even larger disk. In this way, we can actually extend the definition of zeta to cover every complex number except s equals 1. This is part of what makes talking about the Riemann hypothesis so complicated, because the Riemann hypothesis says that all of the non-trivial zeros of the zeta function lay on this vertical line here. But you can't even define the zeta function on this vertical line here without first talking about analytic continuation. Once we accept the idea of analytic continuation, though, we can start to make sense of the trivial zeros of the zeta function as well. Recall in the last video we talked about how at every negative even number, zeta takes the value 0. So zeta of negative 2 is 0, zeta of negative 4 is 0, and so on. Again, if I tried to use this series definition to evaluate zeta of negative 2, I would get 1 plus 4 plus 9 plus 16 and so on, which certainly isn't 0 or any number for that matter. But if instead you'd play this game where you just hop from one point to another using the Taylor series and eventually make it all the way over here to minus 2, what you'll find is that you get the value exactly 0 here. One thing that's underlying all of this is the fact that even though nominally you're making choices about where to start, where to take the Taylor series and extend, no matter how you do it, you'll actually always get the same value when you get over here to minus 2. Namely, you'll always get that zeta of minus 2 is 0. You'll often encounter the analytic continuation of the zeta function in another context as well. One idea you'll encounter often in the math pop culture genre is this idea that if you take this series 1 plus 2 plus ... then you get the value minus a 12th, which is pretty upsetting because pretty clearly the series diverges. But if we just pretend that this series definition of the zeta function makes sense at minus 1, then we would see that zeta of minus 1 should be 1 plus 2 plus 3 plus 4 and so on. On the other hand, using analytic continuation, we can just compute directly that zeta of minus 1 happens to be exactly minus a 12th. Of course, we had to pretend that this series definition made sense at minus 1, which I want to remind you again, it does not. Mathematicians, at least as far back as Ramanujan, have been attempting to find a relationship between this series and the value minus 1/12, or this series and the value 0. And it has proven very difficult to make rigorous progress in this direction. I'll link to a blog post by Terry Tao that goes into some of the progress that has been made in this endeavor. I'll also link to a Mathologer video on this topic.
Bridgestone Turanza 6. At the Comfort Testing Station, we evaluate how well the tires reduce impact over a bumpy road. The results show that Bridgestone Turanza 6 reduces impact force more effectively thanks to its new structural design and softer compound. It optimizes vibration and improves performance by up to 8% compared to the predecessor. Bridgestone Turanza 6. Make every road your comfort zone.
Before we wrap up, I want to talk about what can go wrong here. Everything we've done so far works out surprisingly nicely for the zeta function, but for some other familiar functions, interesting and unexpected things happen. First up, I want to talk about the function f of x equals absolute value of x, which is defined on all of the real line. What if I try and extend this function to the whole complex plane using the methods we've talked about? If you've thought about complex numbers much before, you've probably encountered the fact that the absolute value already has a natural extension to the complex plane. Namely, the absolute value of a complex number is meant to be the distance from that number to the number 0 in the complex plane. So, for example, the absolute value of the complex number 3 plus 4i is supposed to be 5. Based on what we've done so far, you might hope that if we start with our definition of the real absolute value and extend it, that we'll get this notion of the complex absolute value for free. Unfortunately, this is not going to go so well. But let's see what happens. So we'll start here by looking at the Maclaurin series for absolute value of x. That is, the Taylor series here centered at 0. Immediately, though, there's a problem, because in order to calculate this series, I need to calculate the derivatives of this function at 0. And owing to this corner here, absolute value of x does not have a derivative at x equals 0. We talked earlier about things polynomial functions can't do, like having a vertical asymptote. Another thing that polynomial functions can't do is make this right turn that absolute value does here. This, though, is a very solvable problem, because we can just shift the center of our series from 0 over here to, let's say, x equals 2. Here, we can take as many derivatives of absolute value as we like, and they follow this simple pattern. The first derivative is 1, the second derivative is 0, the third derivative is 0, and so on. Putting this into our Taylor series formula, we obtain the not too sophisticated Taylor series for absolute value of x centered at 2x. Drawing the graph of the function x on top of the graph of absolute value of x, we see that it works on this side, but not over here. The way to interpret what has happened here is that the Taylor series is telling us that if a function looks like this over here, then that function should just be the function x. Remember earlier we talked about the rigidity of complex functions, meaning that it was not possible to adjust the value of a complex function at one place without also changing it everywhere else. What you're seeing now is that this isn't true of real functions. We can easily bend and wiggle this side of the graph over here without affecting this part of the graph over here at all. But complex numbers will simply not let us get away with this. And as soon as we set this tiny piece of the graph, the magic of analytic continuation forces the entire rest of the graph into place. Now let's shift our focus to another familiar function. Natural log is a function initially defined on the positive real line. It has a singularity here at x equals 0, owing to this vertical asymptote in the graph. Much like we did with the zeta function, though, we can use analytic continuation to extend this function around the singularity and evaluate the natural log of negative numbers. Again, I want to stress we're not really thinking about what it would mean to take the natural log of a negative number. We're just looking at the shape of the graph that's forced by the rigidity of this complex function. So let's try and figure out what the natural log of negative 1 is. We'll start over here at x equals 1, and then use the Taylor series to define the natural log and its derivatives inside this disk in the complex plane. We hop up here and repeat, then over here, and then finally we land at x equals minus 1. And looking at the decimal values, we find that the natural log of minus 1 should be about 3.141592i. Well, that looks awfully suspicious. The natural log of minus 1 is supposed to be pi I? Let's throw even more fuel on the fire and go back to finding the natural log of negative 1. We again start at x equals 1, but this time we'll hop here instead, and then here, and then to minus 1. Now, looking at the decimal values, we seem to be seeing that the natural log of -1 is negative pi I. But wait, which is it? Is it plus pi I or minus pi I? As we're going to see, the answer is kind of both. Even worse. Let's say I start here at 1 and go from here to here to here to here, and then come back here. This now seems to be telling me that the natural log of 1 is 2 pi I, even though the entire basis of this calculation was starting with the fact that the natural log of 1 is equal to 0. What's happening here is this. Analytic continuation in general only works locally, not globally. What I mean by that is that when we do analytic continuation, we're plotting a path from our starting point to our ending point and defining our function in a meaningful and consistent way all along that path. However, in general, if I take two different paths, I may end up getting different outcomes. This path dependence, however, is not as bad as it may first seem. Indeed, if I wiggle the path however I like, the resulting value will not change as long as I'm careful not to wiggle the path across a singularity. Visualizing a complex function is tricky because ostensibly the graph exists in four-dimensional space, 2 dimensions of input and 2 dimensions of output. So I'm going to help you visualize this in a couple ways. One way is to show the value of a complex function at a point in text like this. As I move this point around, we can see the output value changing. Another way is to show a second complex plane for the output, so that as I wiggle the input over here, you can see the matching output wiggling over here. Note here I'm showing you the same thing in two different ways. This is just a numerical representation of this point over here. So this is two different ways of showing you the same information. If I now split the path in a bunch of pieces and zoom them around like this, and eventually return them all to 1, we see that they all agree with us that the natural log of 1 is 0. But if instead I were to take any of these paths, then when I return to 1, I'll find that the value of the natural log of 1 is 2 pi I. The reason that these two paths are allowed to give different answers is because if I try and wiggle this path into this path, I have to pull the path across this singularity, which fundamentally changes the nature of the function. All of these paths give the same answer because I can change one into the other without doing that. And the same goes for these paths. The idea that the natural log of 1 is somehow simultaneously 0 and 2 pi I challenges our notion of a function, as when we learn about functions, the fundamental property a function is supposed to have is that every input has only one output. The thing we get out of analytic continuation, though, doesn't always respect that. Indeed, the analytic continuation of natural log actually assigns infinitely many distinct values to the natural log of 1. We'll make sense of that in the next video. But to end on here, I want to show you that this notion of a multi-valued function often actually makes quite a bit of sense. Here's the graph of square root of x. It has a singularity here at x equals 0, owing not to an asymptote, as we've seen before, but to this vertical tangent line, which means that the derivative here is undefined at 0. So we cannot make a Maclaurin series out of this function. So let's hop over here to 4 and shift our view to the complex plane. The square root of 4 is 2. As before, we'll let this point wander around the singularity and continue to track its value as it meanders its way back to the point 4 where we started. We see, though, that upon returning to 4, our function now takes the value minus 2. If we allow ourselves to continue to wander around the singularity again, then when we return back here, we've again returned to the value plus 2. The analytic continuation of the square root function is actually bivalued, and the two values corresponding to an input z0 are precisely the two square roots of that number. In a weird way, the calculus of the complex numbers here have identified the meaning of the square root function and helpfully identified that 2 is not the only square root of 4. The number minus 2 is also a square root of 4. I still find this quite amazing. To wrap up, I want to remind you that the functions we started with, sine of x, tangent of x, and especially zeta of s, do not have any of these issues. Zeta of s is a single-valued function, even on the complex plane. No matter where you start and how you let this point wander around the singularity of zeta at s equals 1, the values we find for zeta at a particular input will always be the same. Next time on Zeta Math, we'll tackle the other half of calculus, integrals. Integration will prove essential in our calculations with the zeta function, and will help us understand how, with the help of computers, humans have been able to verify the Riemann hypothesis for at least the first 10 trillion zeros of the zeta function. We here at the channel appreciate all the nice comments we receive. If you like what you see here, please continue to leave nice comments. These videos are a lot of work for us. If you haven't already, why don't you go ahead and subscribe? And if you have any friends who you think would enjoy this content, please let them know. We're almost at 1,000 subscribers, and it would be great to hit that threshold before our next video. If you want to contact the channel, our email is zetamathvideos@gmail.com. That's all for now. Thanks for stopping by, and I'll see you next time.
したら「オッケー」じゃなくてもっと上行こうみたいな感じですっごいニッコニコで楽しそうなのを伝えないといけないと思うのでアイドルなんですね。うまくいかない